Welcome, dynamic students. This mini lecture is a demo of some problems that are concerned with planar rigid body motion. So at this point in your course, you should have done some work with particle or motion of a rigid body that can be considered a particle at its center of mass. Now we're going to leverage that and look at a rigid body only rigid. So the distance between any set of points, 2 points on that body, stays the same throughout the motion, but now the body can rotate. So we have two sources of motion for any point. One, the whole body moving, which is what we captured with our center of mass motion, but then we have to think about the motion that's due to that body rotating, maybe like about its own center of mass, that creates an additional motion of one particle or 1 point, on the body relative to the other. And so one of the best ways to capture that is to use an expression. We're going to look for this problem, we're going to look at velocity only. But we can leverage the fact that a rigid body has the same spacing between any points, and if it's moving in a single plane, we can write an expression for the velocity of any point B on that rigid body in terms of the velocity of another point A, which maybe we presumably know more about, plus the angular velocity of the body, the whole rigid body, which, because we're in planar motion, is going to be oriented outside of the plane of motion, and we're assuming motion is occurring only like in the XY plane, like the plane of my screen. So the rotation of that body is, by definition of planar motion, always going to be into or out of the screen, which I'm denoting as k hat, or z out of the screen, crossed into a radius vector from the point for which I know the velocity to the point for which I don't know it. So this is, I'm just going to put a circle around it so we remember it. This is our general expression, which you can derive from simply the definition of what a rigid body is, points having to stay the same distance throughout motion, and planar motion, which says basically you are only changing positions in one plane. And so you really, if you know rotational velocity and you know the motion of any other point, you can infer the motion of any other point. They all kind of move in lockstep, so to speak. So those two thoughts are how you derive this expression. So we're not going to derive it again for this problem demo. We're just going to put it to work. There are some probably other notes in your textbooks or in your class notes that might go through that derivation, and if that helps you, I would definitely encourage you to do that. But in this demo, we're going to put that to work, that principle to work, and we're going to look for the velocity of different parts of a simple machine. So we have a hinge that's bolted to the wall, and we have a rod, and we'll call the hinge point here A, and we'll call the rod connection point B. And this is attached, this is similar to what's called, I believe, a crank arm in a lot of internal combustion engines, which is probably why this problem was used in a popular textbook. And so this second rod is connected to a cylinder, which is moving in a groove or in a bearing slot. So this doesn't necessarily have to be a combustion engine. It could be any kind of machine where we have one part that's moving on a prescribed path. This could be a bearing race. This could be anything, any kind of path that controls motion. And then we have two rigid body connectors that are connected to another fixed point, the ground, something very rigid. So the little dashes denote a rigid, firm surface, which you can think of that as your reference frame, your inertial reference frame, the ground, the side of the building, something that isn't moving, as opposed to our rigid bodies, AB, and then we've got another rod, we'll call it BC, where point C is in the middle of this cylinder. And so we know something We know something about the motion and the dimensions. We'll start with dimensions. From A to B is 2 feet. And then B to C, that dimension is 3 feet. And most of these types of problems concern themselves with motion at a given snapshot instant. So in this case, we're looking at these rods are both moving. The cylinder is moving down. The cylinder is moving downwards at 4 feet per second. And so we want to know something about the motion of these two rods at this instant in time at which this angle is 30 degrees and rod AB is making a right angle to the wall. Now obviously if we were going to continue that cylinder's descent down its groove, we could recalculate everything again and again and again for every different position. And in fact, if we set up some equations of motion and we wanted to know those values at different points, it wouldn't be that hard to maybe use our equations of motion to write an algorithm so a computer could calculate that. But it would start with getting relationships between positions, sizes, and ultimately velocities of different points on these rods. So even though we're calculating this for a single instant in time, we're laying the groundwork to capture that motion for any instant in time. So this is, I know it seems a little contrived that we're just looking at it this one instant when in actuality it's moving through an infinitude of positions, but it's something that we can build on. Okay, so if we want to apply our general relationship of motion here, we want to relate, in this case, we know how C is moving. Maybe it is a linear motion, so it's probably fairly easy to measure. We know what our geometry is, both our length dimensions, and we know our angles. We could set a coordinate system. Since we're going to be involving cross products, it's really useful. And I personally like to just stick with a default coordinate system. With my I hat or X direction to the right and my J hat going up. Generally speaking, you're going to want to put your coordinate system oriented such that you make the problem easy. If I don't see an obvious way to put something, I try to use my coordinate system in a consistent manner so that I'm less likely to make sign errors. With it this way, increasing theta, which means the direction of omega, is going to be counterclockwise. So I draw a little arrow saying theta, and this also means I cross J, K hat is effectively pointing out of the screen. And so that'll be important for looking at the signs of omega. So let's see, what else do we know and want to know? I believe that the question, which comes from the Hibbler 14th edition textbook, this is problem 1658 if anybody wants to follow along and happens to have that book. Somebody gave us this information and they wanted to know something about the rotational velocity of this rod. They wanted to know omega AB. So this is, of course, this is a fixed axis rotation, and we know that BC may be rotating too, so we may need to find that out as part of the problem. So let's see how we can apply this real simple relationship, starting with what we know and what we don't know, and get the information that we need for whatever reason. Why they would need to know that rotational velocity, I don't know, maybe they're sizing some kind of sensor that's going to track it, or maybe maybe they know the mass of this and they're trying to design a bearing at A. There's a lot of reasons why they might need to know that. Definitely we know that that is related to acceleration of a point, so maybe they're designing materials for our hinge bearings A and B. That would be a very practical reason for wanting to know that particular piece of information. if you notice, these are very general problems that probably, could generate a lot of different uses. So they won't all have necessarily a single practical application. So let's start by thinking about points at which point that make good reference points for velocity, where we may know what the velocity is, because honestly, we're again in the game of equations and unknowns. For every one of these expressions we can write, remember we're in 2D, so we can get two equations out of each one in the I hat direction and one in the j hat. So presumably if we knew the velocity of two different points in the problem, we generate four equations. So we could solve for four unknowns, which we might need. So we can start over here at A, which is a fixed point of, it's fixed rotation, our bar AB about point A. So we know that the velocity of A is 0. It's fixed at the hinge. It's bolted to the wall. So we could write the velocity of point B, which is on this same rigid body, right? We can use our relationship of one point on a rigid body to the other. We can say, okay, B is on the same rigid body as A. So I can invoke this expression. BA plus omega AB K hat cross RAB. Okay, so we know that because it's a fixed pivot, VA is 0. That's real convenient, and given the geometry of the problem and our chosen coordinate system, we can write the radius vector from A to B fairly easily. It's 2 feet I hat. So our velocity of point B is simply equal to the angular velocity of that rod AB, which we know is in the k hat direction. It's either positive or negative, cross 2 feet I hat, which is equal to the magnitude of our angular velocity times 2 feet times k hat cross I hat. So if we apply our right hand rule and we put our fingers out and pointing out of the screen and we curl them over towards our I vector, our thumb is pointing in the direction of our j hat in the positive direction, so we can replace this with positive j hat. So the velocity of point B is equal to whatever the angular velocity of rod AB is times 2 feet, and it's oriented at this snapshot in time is oriented exclusively in the j hat direction, which if you think about it, if this rod is pointing straight in the I hat direction, it's fixed point rotation, it kind of makes sense that it's going to be pointing straight up or down at that instant. If this were not a right angle here, it would have an I hat component. We can do a quick units check. And remember that angular velocity is going to be in radians per second, which can be thought of as per second. We have 2 feet, so we have feet per second, which is what we'd want for velocity. We can extrapolate and say that we know, basically VB, I hat equals 0, but we still basically have two unknowns. We have the magnitude of velocity B and we have the magnitude of our angular acceleration. So we need more information. And we haven't taken advantage of what's going on over here at point C. So to get to point C, we kind of have to take a look at what's going on with yet another rigid body. Because point C is not attached to the same rigid body as point A, because we got a hinge here at B. It is definitely not rigid. B is a hinge. It's freely rotating. But we can go ahead and say something about the motion at point C versus the motion at point B. We can treat rigid body BC the same way we did rigid body AB. It's another rigid body. We can do the same thing. And it just so happens we know something about the motion of point C. It's 4 feet per second straight down, j hat direction. So that gives us something to put in for our reference. So let's go ahead and apply that, and let's write an expression for VB. It's the same VB, but we're looking at VB from the point of view of C on a different rigid body. So we can just invoke this, plus, and of course it's the angular rotation of a different rigid body. We got rigid body BC is rotating somehow, but we know it's rotating in the k hat direction because this is planar motion. And then we have the radius from C to B. We're going to cross that. Okay. We know this is 4 feet j hat negative. And we can use some geometry to get our 30 degrees and our 3 feet to get the radius vector from C to B. We're going to go, it's going to be negative in both directions, so we're going to have negative 3 feet cosine 30 degrees I hat minus 3 feet sine 30 degrees j hat. So that's our radius vector from C to B. So we can write, we're going to cross omega BC k hat into this radius vector. So we're going to end up with omega BC times negative 3 feet cosine 30 degrees times k hat cross I hat plus omega BC times negative 3 feet sine 30 is our j component times k hat cross j hat. And we already looked at the cross product of k hat cross I hat. We know that's going to give us a positive j hat. If we look at k hat cross j hat, we can do the right hand rule again. I got my right hand. I'm going to point my fingers outside, like out of the screen towards me. And I'm going to flip them over, and I'm going to curl my fingers in the direction of the j hat axis, and my thumb is pointing in the negative I hat. So this is negative I hat. And if you do a lot of these problems with rigid body motion, you'll find yourself doing k hat cross I hat and k hat cross j hat a lot as you go through these expressions relating acceleration and velocity of one point on a rigid body to another point on the same rigid body. Can't emphasize this enough. This relies on being on the same rigid body. It's literally defined around the properties of 2 points on the same rigid body. So that's why I changed colors. We're on a different rigid body. We're on the green body. Okay, so, and this is all equal to the full vector VB. Okay. So let's see, we had one equation up here and two unknowns. Now we've got another equation, and I'm going to use red to start tallying things up when we're looking at unknowns. Actually, let me go back to blue here to do my tally. So this is the magnitude of VB times j hat. Okay. So here I have one equation, and I have two unknowns, namely the magnitude of the velocity of B. I know its direction, it's all in the j hat, and then I have the magnitude of my angular velocity of rod AB. Okay. Down here, I've got basically I have another unknown, but it's the same one I already knew before. And then I've introduced a new unknown. this expression, because I can write an expression in the I hat direction and the j hat direction separately, because two orthogonal directions, they're independent of one another basically. I get two equations down here. And I've introduced one additional unknown in the form of omega CB. So I've got one equation, two equations, so that's three equations, and then I have 1, 2, 3 unknowns. I can solve for everything I need to know about this problem. I've got it. Now it's just kind of cranking through the math, cranking through the vector algebra and some just basic algebra, which we'll go ahead and do. But that was the important point, is figuring out how many unknowns that I have based on my expressions of motion, and how many things I need to know about motions of different points. So it was key, in order to deploy this equation properly so I could get an answer, I had to know something else about the motion of a point on the rigid body. I had to know that I had zero motion at A. I had to recognize that as a fixed pivot and say, hey, that velocity is zero because it's bolted to the wall. I also had to be given velocity C over here. And then the last point is I had to recognize that B is actually attached to two rigid bodies. So I can replicate this expression from the viewpoint of body BC and body AB, and accepting that I'm going to generate another unknown. But now I know the rotational. I can get the rotational velocity of both rigid bodies, which I might need to know for something. So the next thing I'm going to do is I'm going to take this whole equation and I'm going to write it in terms of just I hat and j. Well, I hat and j hat components. I'm going to basically collect terms. So let's see, let's start with our j hat, and we know that B basically is in the j hat direction. So I'm going to say VB j hat is equal to -4 feet j hat. And I could have dropped the unit vectors, but I'm leaving them just because it's so easy to make a mistake and forget what I'm doing. So I'm leaving them on here just to remind myself that that's the vector direction I'm concerned with. So let's see. This was a positive. I've got a -3 feet, which I have brought down there. So I'm going to try not to make a sign error. 3 feet, cosine 30 degrees, j hat, and no more j hat terms. Okay, so here's one independent equation. Now I'm going to replicate this for I hat. So I could say, assuming that VB had an I hat component, it doesn't, but if it did, I would write it like this. And so we've only got one set of terms here. So we have negative omega BC times 3 feet sine theta, or excuse me, sine 30 degrees, not theta, we know what that angle is, times negative I hat. One negative, two negatives, so we end up with a positive. As it turns out, it doesn't really matter what those signs are, because we know, now we can switch over here. We know that VB I hat equals 0, and so we can basically say, therefore 0 equals omega BC times 3 feet sine 30. This can only be true if that's 0. So at this particular instant, this rigid body it's not rotating about its own axis. That actually has to be 0 at that instant. Later on in the motion, I'm sure it probably isn't, but at that point it's actually 0. So what that means is we can use this fact And we can substitute back over here and say that's 0. So now we can relate our VB magnitude to the velocity of c. So we now have an expression for VB, and it's just 4 feet. So we can go ahead and back substitute that over here and get an expression for our WAB. Checking notes to make sure got things going right. So I'll continue in the blue. So if our VB whole vector is -4 feet j hat, which is equal to omega AB times 2 feet j hat, then omega AB has to be negative equals negative. Feet get canceled. -2 radians per second k hat, effectively. Vector. So the negative sign means it's rotating in the direction of that green arrow, because a positive angular velocity or angular displacement velocity and acceleration is all going counterclockwise. We got a negative number here. That means it's rotating clockwise, which is consistent with B going downwards and C going downwards. So now we know pretty much everything. We know the angular velocity of this rod. We know the angular velocity of this rod. We know the velocity of point B, velocity of point C. We know that A's velocity is 0. It's still attached to the wall. And we would be ready to use this, these angular velocities if we wanted to move on and calculate something about acceleration, which we won't do as part of the problem, but that is a component of the similar analogous expression that relates acceleration at any 2 points on the same rigid body. So that'll be coming up in other demos and probably homeworks in your study of dynamics. So that ends this demo problem, and please stay tuned for more exciting rigid body planar motion.